Now, what's a black body? How do we understand a black body? A black body is a body that can absorb all wavelengths, or that can absorb all the frequencies that are falling on it. And this when this black body is heated, it can emit all wavelengths, it can emit all frequencies. So this is what black body is, and we cannot have an ideal black body. We can have some approximations where we can have a body which is close to be the black body. Now, here in this video, I want to talk about the Lumer and Prinsham experiment. And what they did, they tried to investigate the radiations that are coming from a black body. So we have a black body, okay, this from here, from this slit S1, the radiations fall. They fall on this M1. This M1 is a reflector, and then the reflected radiations are subjected to a prism, and then these radiations are received by M2, and these radiations are further reflected by this concave mirror M2 that's placed here. And from here, the reflected radiations are received by a detector, and this detector has it has a galvanometer that can detect the signal. And this arrangement, this measurement can be done throughout the course of 360 degree. So this is how the things the things of the original experiment that was conducted by Lumer and Prinsham look like. And this table that I'm talking about, it can be rotated slowly, so that different parts of the radiation of the spectrum successfully fall on this detector, and corresponding deflections that we'll have in the galvanometer connected to this detector, and the intensity of each line is proportional to the deflection that's measured by the galvanometer. And what we do is, from this experiment, they came up with certain results, and we would like to draw these results and what were the outcomes of those results. And what they did is they obtained the result in terms of energy and in terms of the wavelength, and the behavior of the output was like this. It was like this for another temperature. It's approximately like this, and this is E lambda. This is the energy, and we can see we have here peaks in all these curves, and let me assume that this peak of radiation is at wavelength lambda m1, and say this peak is at the wavelength lambda m2, and similarly the third peak that we have in the third curve is lambda 3. Now this lambda is maximum. It is the maximum value of lambda. So all these dots that I'm showing here, I'm trying to put the peak of these curves, and the black body is heated, and this black body is heated, and the radiations are received and detected through this experimental setup. And this is the outcome of that, the rough outcome of that experiment. And here, this curve is for, say, T3, and this curve is for T2, and this curve is for T1, such that this T3 is greater than that of T2, is greater than that of T1. Now, what is the outcome? What are these observations? The very first important point is that 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 the energy is not uniformly distributed. You don't have a uniform distribution of energy that you could have expected. It's not uniform, right? So the spectrum is non-uniform. You can see that it has a peak and then it goes down, and at a given temperature we have at a given temperature the intensity of this radiation increases. So T3 is the greatest of the all. So we can see that the intensity of radiation increases with increase of the wavelength and becomes maximum. Okay, it's maximum for a particular temperature. It has a maximum value, then it goes down. For another particular temperature it has a maximum, then it goes down, and further increasing the wavelength, in the intensity of heat radiations, that goes on decreasing. Where further increasing the wavelength, there is decrease in the energy. And we can see here that an increase in the temperature. See, we have three curves here, and we have three different peaks, and we can see the lambda max for T1 is smallest, and lambda max for T2 is more than that of T1, is more than that of T3. So I can say here that an increase in the temperature causes decrease in lambda m. So you can see that lambda m is shifting towards left, such that this lambda m times that particular temperature is always a constant. And this is what is the famous Wayne's law that we have. And then talking about an increase in temperature causes an increase in energy emission for all emissions. So this is the curve for T1, this is the curve for T2. So in overall, we can see every curve is coming up with more and more energy. So the increase in temperature, it automatically causes an increase in the energy emission of this black body. And the area under each curve, if we take the area of this curve, then the area of this curve, the area under each curve represents the total energy emitted by the body at that particular temperature on which you have taken the readings, on which you have taken the data. So what does it mean here is that that it is found that this area, that suppose I take T1, area of T1, this area is directly proportional to the fourth power of the absolute temperature. Now, what I said before is that the area that is covered by this curve, this gives us the measure of energy that has been emitted by the black body. So what we find is that this energy which is given by the area that's enclosed by this curve, this area of the graph T1 that is enclosed, this gives me the energy emitted by the black body. This energy is found to be proportional to the fourth power of temperature, and this is what is known as Stephen's law. Now, these are the observations. These are the observations of Lumer and Pringsham. What they observed when they set up their experimental setup. These were the outcomes of that experiment, which we have talked about in detail here. But the classical module that was used to explain the behavior of black body radiation, when it was used to explain these curves, it perfectly failed. It worked in certain areas. One thing worked in certain areas, say Rayleigh-Jean's law. It works in some area, but it does not work in some other area. So these curves that were obtained by performing this experiment could not be satisfactorily explained by the classical laws of radiation. They could not be explained perfectly, and the solution to this problem was given by Max Planck, and it was Max Planck who explained this behavior of the radiation, the energy of the radiation emitted by the black body.